Hello everyone, this is 5.1 exponential functions and their graphs. And I first want to get started by talking about what an exponential function even is. And it's merely a function of the form b to the x, where b is a positive real number, so bigger than 0, and not equal to 1. The reason why I want to look at these cases is because x can be any number. The exponent can be any number. So if x is, let's say, 1/2, what do you want your base to be? You do not want your base to be negative, because if you have a negative number, well, then you get -1 to the 1/2, for instance, which is, if you remember, the square root of -1, because 1/2 power means square root, and you just get I, which is not real. So this is kind of a setup for failure in the sense that we won't go from real numbers to real numbers, we'll go from real numbers to imaginary numbers. So for that reason, we're not going to consider the base to be negative. We're only going to consider nice cases where the base is positive. Also not 1. Why? Well, that's kind of obvious. When it's 1, it's really easy. 1 to any power is just 1. So it's a not a very interesting case there. So we're considering this for the base, positive and not equal to 1. Now for the graph, well, there's two cases. Either the base is bigger than 1 or it's less than 1. And of course, since it's positive, it's going to be in between 0 and 1 as a consequence. But in the case that it's bigger than 1, it's going to be an increasing function like this. Its y-intercept will be at y equals 1 because, of course, when you plug in 0, b to any number to the 0 is 1. So you get 1. Similarly, for when it's less than 1, when the base is less than 1, instead of increasing, it'll decrease now. And it will also have a y-intercept of 1 because, again, any number, whether the number is bigger than 1 or less than 1, to the 0 is 1. Okay? And this is what the graphs have in common. They both have a horizontal asymptote at the y-axis, or at the x-axis, I meant to say. Y equals 0 is the equation for the x-axis. They both have y-intercepts 0, 1, like we just saw. They both have a domain of -infinity to infinity, so you can plug in any real number on the x-axis into them, but the result will only be positive, it won't be negative, which makes sense because both of them are positive bases after all, and a positive number to any power is still positive. So the domain and range should make sense. 1 to 1. They're both 1 to 1. They both pass the horizontal line test. Now, why that's the case is because either it's purely increasing or purely decreasing. There are ways of proving this with calculus, actually, but a non-calculus way of viewing this is pick a base, either bigger than 1 or less than 1, let's say like 3 or 1/2 or something like that, and see what happens when you take that number to different powers. So you're not changing the base, you're changing the power. So if you stick with 2, that's this case. Or 3, I think I said 3. But let's say you stick with 3 as your base. You change the power. As the power gets larger and larger and larger, 3 to that number will get larger and larger and larger as well. But on the other hand, if you pick something less than 1, the opposite will happen. It'll keep decreasing. So since it continuously decreases, there's no up and down movement, so there's no way it can fail the horizontal line test, which would make it a 1-to-1 function. So now we'll take a look at some specific examples of graphing. Right, so here I think are pretty decent examples to consider graphing. Let's graph first 2 to the x and then 1/2 to the x. Here, of course, the base is bigger than 1, and here, of course, the base is less than 1. So let's see what happens, and let's graph each of these by method of table. So the x values I want to take a look at are the kind of obvious ones. -2, -1, 0, 1, and 2. We'll see what f of x is for each of these cases. And we'll also do the same for this one here. I should have labeled this as 2, by the way. So let's do -2, x equals -1, x equals 0, 1, and 2. Good. And let's find out what f of x is. Perfect. So when we plug in these numbers, first let's plug in 0. So let's start off with 0 and positive. So 2 to the 0 is 1, we saw that earlier. 2 to the 1 is 2, and 2 to the 2 is 4. And you know what, let's go down to 3, might as well. 2 to the 3 will be 8. So you can kind of see how large these numbers get. And as the x values get larger and larger, 2 to any power will be larger and larger as well. What about negative though? Well, 2 to the -1 is the reciprocal of 2, which is 1/2. Okay, fair enough. What is 2 to the -2? Well, 2 to the -2 is the reciprocal of 2 to the 2. 2 to the 2 is 4, so this is 1/4, naturally. All right, so now let's graph these. well, I guess plot these to see the graph is what I meant to say. So we got -2, -1, 1, 2, and 3 for the x's. And for the y's, well, remember they're non-negative, so we're going to start in the positive direction here. So let's get up to 8, I think, for the y's. Let's do 1, 2, 3, 4, 5, 6, 7, and 8. Like that, I think sounds good. Now, again, x equals -2, y is going to be 1/4, which is about there, a quarter of the way in between. -1 will correspond to 1/2, 0 will correspond to 1, 1 will correspond to 2, 2 will correspond to 4. So we see what I'm doing, just following the table here. 3 corresponds to 8. So we indeed see it shaping up to look like what I just described previously. And let me connect them in red, I guess. So I'm trying to be as smooth as possible so we can see it. But we indeed get this. And you can see that as the x values get more and more negative, we're going to get reciprocals of large powers of 2, and it's going to get closer and closer to 0, but still remain positive because there's no negatives involved. Perfect. Now on the flip side here, there's actually a really nice way of seeing this. And the really nice way of seeing this is that 1/2 to a negative power reciprocates it, and you get back this same table, but in reverse. So 1/2 to the -2 is the reciprocal of 1/2 to the 2, which is 2 to the 2, which is just 4. Same thing for -1. 1/2 to the 0 is just 1. 1/2 to the 1 is 1/2, and 1/2 to the 2 is, well, 1/4. So you literally just get this same table but flipped. And if we had shown -3 here, well, 1/2 to the -3 is the reciprocal of 1/2 to the 3, which is 2 to the 3, which is 8. So we indeed get this same image, but flipped. So instead of increasing, it'll be decreasing. So just to show that, let's see if we have space for it. So we're going up to 4, I guess, in this case. And let's see. So -2 corresponds to 4. -1 corresponds to 2. We have 0, 1, 1, 1/2, and 2, 1/4. So indeed we get the exact opposite shape, the one that we suspected we would get based on the previous discussion, and we do. And in fact, there's a really nice way of seeing this, like I mentioned earlier. The y values are just flipped, and believe it or not, this is actually a transformation we saw. We can write this as 2 to the -1 to the x, which is just 2 to the -x. And if you compare these two, what do you notice? The only difference is there's a negative in front of x. When there's a negative in front of x, what happens? What's the transformation? There's a horizontal flip, and that's exactly what the image is doing. It's flipping across the y-axis. So there's no surprise from the transformation perspective. So I hope that explanation was clear. So in fact, this should tell you, even though I picked 2 and 1/2, which are reciprocals, this actually works no matter what numbers you pick. Because since if you pick a number less than 1, you can always write it as 1 over any number bigger than 1, and any number bigger than 1, or whatever that number would be, would have a graph like this. So it's natural that they would have reflective graphs because of this phenomenon here. So now we're going to do some examples based on some property. I'll show the property first, and it has to do with 1-to-1. I said 1-to-1 is an important feature of these graphs, and let's see why now. All right, so now finally for this 1-to-1 property that I've been hyping up, let's see what it's about. So remember the 1-to-1, for a function to be 1-to-1 means the following is true. In general, it says if f of x1 is equal to f of x2, then x1 must be equal to x2. In other words, if you have the same y values, you must have the same x values. If you have different x values for the same y value, well, then you won't pass the horizontal line test, if that makes sense. So if you think of like a parabola, parabolas fail, so I guess I could draw a picture here. Parabolas fail the horizontal line test because there exist 2 points that will correspond to the same y values but have different x values. So here, these are different x1 and x2, but they actually have the same y value, and if this is the curve of f, then these will each be f of x1, but it'll also be equal to f of x2. So here f of x1 is equal to f of x2, but x1 and x2 are different, they're not the same. So this is now 1-to-1. This fails the horizontal line test. But to pass the horizontal line test, this must be true. What does that mean specifically for exponential functions, though? It means the following. If we have b to the x1 being equal to b to the x2, then this will imply that the exponents must be the same. So that is, this is actually a pretty important observation here, the bases must be the same. So if you have the same base, so let me write it like this, same base, then what does this imply? This implies you have the same exponent. So if the base is the same, then the exponent's the same. Of course, this is only if the base is like we saw previously. Meaning, if the base is positive and not equal to 1, then this is true. If it's equal to 1, it's totally not true, because 1 to the 3 is equal to 1 to the 5. If it's negative, who knows? But if it's positive not equal to 1, then this certainly must be true. And now we'll see some examples of this, but we have to have the same base. So what we have to do now is look back at exponent properties. So it wouldn't be a bad idea right now to review some of these exponent properties, and we'll see some of them in action here, but try to do it on your own and try to look back at some of those exponent properties we saw from pre-algebra courses. And let's see if we can apply them here. Let's see. So we want to have the same base. Here, what's the base? It's 3. Here, what's the base? It's 27. Well, the base isn't 27, but the number is 27. So we need to ask ourselves, is 27 3 to the something? And it is. You can write it as 3 to the 3. So if you could write 27 as 3 to the 3, and on this side, this is 3 to the x plus 1, then we can apply the 1-to-1 property. So here I'm writing 1-1, like 1-to-1. So just for shorthand. So the 1-to-1 property here implies what? Well, when you have the same base, this implies that the exponents must be the same. So that means the exponent x plus 1 must be equal to 3. Perfect. So now we can subtract 1, and we'll get x is 2. And of course, you can indeed plug this in to see if it works. When you plug it in, we get 3 to the 2 plus 1, which is 3 to the 3, is equal to 27. It works. What about over here? Well, so there's a few ways of doing this. We need to write 32 as 1/2 to the something. That's tricky. That's really tricky. What you could say is you could say, well, 32 is 2 to the 5th, like this. Maybe that's a fine way of thinking of it. But then we're kind of stuck, because you could say, well, 1/2 is 2 to the -1. And here, if you multiply the exponents, that's an exponent property, you get 2 to the -1 is equal to 2 to the 5th. And now we can say by the 1-to-1 property that we just saw, so 1-to-1 implies that -t is equal to 5. So naturally, dividing by -1 will give us that t is equal to -5. And plugging that in, 1/2 to the -5 is the reciprocal of 1/2, which is 2, to the positive 5. 2 to the 5 is 32, so it works. Another way, of course, of doing this was to right away say that 32 is actually 1/2, which is this base, to the -5. And if you did that, then right away, you can bypass all that work and use the 1-to-1 property to get t is equal to -5 right away. So obviously one way of seeing it is easier than the other, but it's nice to know you can apply properties to kind of get from one step to the next. To me, this makes a little more sense. I'm just following my nose, writing this as the more sensible exponent, and then writing this side as that to the same base that we just found for 32 being 2 to the 5th, opposed to writing 32 as 1/2 to the -5. That's a little harder to see in my opinion. But anyways, there's both of those. And now we're going to see an application of exponents that I think we deserve to see, and it'll actually bring a new number into the scenario. And this new number is used all the time in calculus, so it's a perfect time to introduce it now, and let's take a look. All right, so the application I was talking about, of course, is finance. And the first thing in finance we need to take a look at is what is called compound interest. And compound interest, just to give you an idea of what it is a way of applying a yearly interest rate more times throughout the year than just at the end of the year. If you apply it just at the end of the year and it's a yearly rate, that is called a simple interest. And that has the formula you may have seen before. That would be I is equal to PRT. So that's just the principal times the rate times time. So that'll give you how much interest you've accumulated if you started with this principal amount. The only thing is that that's the interest. If you want to find out the actual amount, well, notice the amount will just be the amount you started with, P, plus PRT at the end of the year. And if it's after 1 year, then T is just 1, so you don't even need that in the equation. And if you factor out P, what do you have? You have 1 plus R. So what I'm trying to explain with this calculation here is more or less where this equation comes from. Of course, it's not R, it's R over N. And that's because the rate is divided into however many periods there are in the year. Usually banks use a period of months, but they could use weeks, days, seconds if they're crazy. But some banks are, who knows. And we're taking this, of course, to the exponent of how many periods we'll be passing in order to figure out how much we'll have at the very end of those amount of periods. So here the compound interest formula is A is equal to P times the quantity 1 plus R over N to the N times T, where A is the amount after T years, so that's the amount you'll have total in the bank, what you initially deposited plus all of your earnings with interest, or if you're borrowing money, how much they'll get from you, how much you owe to them basically. But it's the same idea. So this formula works whether you are investing money or whether you're borrowing money. Same formula is being used. So that's A. P is the principal or initial amount. R is the yearly rate, but you have to put it in decimal. Anytime you have an equation involving a percent number, you want to convert it into decimal in order for the math to work correctly. So in order to multiply things that are in percent, you have to convert them to decimal first. So that's kind of key, which is why I wrote that there. So in decimal, please. Also, N is the amount of times compounded per year. So if it's monthly, it'll be 12 times per year. If it is weekly, it's 52 times per year. If it's daily, it's 365 times per year. There are some kind of funny ones, like if it's compounded every 6 months, how many times per year is that? It's not 6, it's 2, because every 6 months is twice a year. So keep that in mind. There are some funny ways of wording that. And T, of course, is just the number of years total that have passed. So now here we're going to do this example. And here I say, how much will be in an account after 25 years if $32,000 was initially deposited at 3.2% compounded monthly? So we have to figure out what each of these things are. There's 5 things to figure out, so let's just write them down. There's A, P, R, N, and T. Now the one that we don't know right away is A, because that's how much will be in the account after those amount of years. So we don't know the amount after, that's what we want to find, so that'll be our unknown amount. P is our initial amount, and that's 32,000, so that's okay. Good. What about R? Well, let's see, R is the rate. The rate is this in percent, so that's a key thing to look out for is the percent symbol. Moving that into decimal, you move the decimal over to the left twice. So you're going to get a space here, so that's going to be 0.032 after converting to decimal. So just divide by 100 basically. If you type in your calculator 3.2 divided by 100, it'll give you 0.032. N, how many times per year? The keyword here is monthly. If it's compounded monthly, how many months are in a year? 12 months. So if it's compounded monthly, that's 12 times per year. Great. Now finally, how many years? 25 years. So we've looked at all of the key components in the wording here, the sentence, and we've converted and figured out what our labelings are, and now let's just plug into this formula. So now, applying all this into the formula that we've just seen, we have A is equal to 32,000 times 1 plus 0.032 over 12 to the 12 times 25. Now this is calculator time. We're going to apply this into our calculator and let's see what we get. So I just punched this into my calculator and here's what I got. I got 71141 and 52 cents. And you can try this on your own and see if you got this. If you did not get this amount, and notice I'm rounding here to the nearest cent. It was really 51.9, but I round to 52 to for the sense. If you didn't get this, it's 71,000, then chances are what you didn't do correctly in your calculator was, if you wrote this all as one piece, you probably didn't write your exponents in parentheses or even multiply them first. So that's one thing to note. If you multiply these first, 12 times 25, you get whatever that is, which I think is 300, but you could do that on your own. And then you can take this to the 300, then you'll get this. But if you want to do it in one shot in your calculator, you have to write this exponent in parentheses after pressing that exponent caret symbol. So just keep that in mind. But in any event, this is the amount we'll have left after 25 years have passed, provided we haven't, deposited more or taken anything out and just left that $32,000 sitting in there for 25 years. So there we go. And now we're going to take a look at a slightly modified version of this formula, and let's see that right now. All right, so this modification we'll see in due time, but before to see the modification of this formula, what we're really taking a look at is what is called continuous compound interest. And this is the idea that the interest is being applied every second, every millisecond, every so often, basically. It's always being applied continuously. So how will that affect the amount that we have at the very end? And you may think that, well, if you deposit your money and you're getting it continuously compounded, then you'll have infinite amount of money by the end of the year. And that's not true, actually. And I want to show us based on a simple idea posed by Bernoulli, who was a mathematician from, I believe, the 1600s. And basically his idea was this. Well, what if I were to give you $1 rated at 100%, so R is 1 in decimal, for 1 year, and I'm doing it infinitely often? How much will you have at the end of that year? And again, the answer isn't infinite, it's a surprising answer. So, well, let's just see. So if we're letting n go towards infinity, we can plug everything into this expression here, and we'll get a is equal to p is 1, so don't write it. And then in parentheses, we have 1 plus r is 1 over n to the n times 1, because t is 1, so that's to the n. So we have this expression here. And the idea is we want to see what this approaches, what a approaches as n goes to infinity. And we can plug in certain numbers in for n. Like if you plug in n to be 1, well, at the end of 1 year, if you're applying it once, then you'll have, 1 over 1, 1 plus 1 over 1, which is 2 to the 1. So you'll have $2, which makes sense because if you give me the $1 and I give you 100% of that dollar back, in addition to the dollar that you had, because it's interest, then you have your original dollar that you deposited to me, and the interest amount, which is another dollar. It's 100% of the dollar you gave me. So you'll have $2 back. So that makes sense. But what if n is, let's say, 2? If n is 2, well, then it's 1 plus 1 over 2 to the 2. And this we can actually do on the board here. 1 plus 1/2 is 3/2. To the 2 is 9/4, which is actually 2.25. So notice we're compounding it twice as often, but we only gain 25 cents out of doing this. So you can actually try experimenting and plugging different values of n, but I'm just going to tell you what the result is. So actually, as n approaches infinity, a will be approximately, here's what it is. It's 2.71828, and I don't know the rest. You can use your calculator. This number is called E. So this is the new number I was referring to earlier, and this number is used a lot in calculus. It is often known as the natural exponential. It is known as a natural number. It's natural exponential. It is called E for exponential, or sometimes referred to E as Euler's constant. Euler was another mathematician. Of course, it's not named after Bernoulli, which is kind of sad because he came up with the idea. But Euler coined using E to label it, I believe. Bernoulli may have used a different letter to label the number, but that's just the way history goes, I guess, sometimes. Anyways, this is the new number we discovered, It's 2.71828. It's irrational, like pi is irrational. So notice pi is 3.14159 something. E is this, so it's just a new mathematical constant. It's just a new mathematical constant that you may or may not have heard of before, but it's similar to pi in that regard. And now we're going to use this idea of E coming from this expression here as n goes towards infinity. So now we know what it is now. It'll approach E, and we're going to see how we can modify this equation. So we'll do that modification, and then we'll do an example based on the new formula. So I'm going to try my best to show you this modification and prove to you the formula for continuous compound interest in a fairly short amount of time. It's a little sneaky though, so just kind of bear with me. So we want to use this fact here. I'm actually not going to use n though. I'm going to say that it's some other number, and in fact I'll use m. And we're going to ask ourselves what m needs to be in order for us to see it here. And it actually depends on this 1 plus part. So if only this r over n was 1 over m, then we'll have something going for us. So we'll try to go based on that observation first. So if we let r over n be 1 over m, then what can we say? Well, notice in the exponent we have n. We don't have r or m, we have n only. So if you cross multiply to solve for n, you get right away r times n is equal to n times 1. So n is equal to rm from this assumption here. And now applying these two things here, we get the following for a. We get a is p times a quantity 1 plus 1 over m, because r over n is equal to 1 over m, and n times t in the exponent, well, n is equal to r times m, so that's rmt. And now I'm going to rearrange some things here and write this as p times 1 plus 1 over m to the m, then to the rt. So let me see if I can write that a little better. There we go, like that. And this should make a lot of sense. I'm just kind of rearranging the exponents and multiplying exponents, saying that taking a power to a power is multiplying the exponents. And now what? Well, now, what is this? As m goes to infinity, notice, as n goes to infinity, m would go to infinity as well. R isn't going to infinity, r is kind of staying the same. So this will approach E. Good. And what we have now is this formula, P times E to the RT. Oftentimes people remember this as a pert, but this is actually the continuous compound interest formula. A equals P to the RT. N doesn't matter because n is going towards infinity, and as n approaches infinity, we just get E as a constant. So now we're going to see some examples using this. All right, so again, this is the formula for continuous compound interest. A equals P E to the RT. And A, P, R, and T are the same as they were before. A is the amount after, P is the principal, R is the yearly interest rate, and T is the time that has passed in years. And let's take a look at this example now. Here we say on the day of childbirth, a parent deposits $30,000 in a trust fund that pays 5% interest compounded continuously. And we want to determine the balance in this account on the child's 18th birthday. So really what we have from this is our initial amount, principal, is $30,000. Our rate, yearly rate, is 5%, so that's 0.05 if you write that in decimal. 5 divided by 100 is 0.05. And how much time has passed is, of course, 18 years. Applying each of these into our formula, we'll have A is equal to 30,000 times E to the R times T. And if you're using your calculator, just like I am, you'll get 73788 and 9 cents if you round. By the way, there's two locations, at least on my calculator. I'm using TI-83 plus. There's two locations for E. One is second division, and the other one is second ln. If you press second ln, it'll actually give you a spot for the exponent. So it looks something like this. E to the, and then it'll actually say, so it'll just be this. So it'll actually ask, what's the exponent? And if you type this in your calculator, 30,000, and then this, then all you need to do is type 0.05 times 8. In other words, the parentheses for the exponent are already there for us. So there's no room for error like there was for from the previous formula for just regular compound interest. So for continuous compound interest, to be honest, it's a little easier in my opinion. There's less to figure out as far as labeling themes. There's only only 3 themes instead of 4 from the previous one. Well, I guess technically there are 4 here because we don't know what A is, but there's 1 less basically. And the formula is just a lot nicer. So there's that example. I only wanted to do 1 example for this, and I believe that's actually it. But I want to do 1 more example, and I'm going to do an example involving E now. So I'm going to combine basically what we saw here with what we saw when we solved. So let's see if we can figure that out. Right, so here's the example I wanted to do. It's a 2-parter. The second part actually involves E. The first part here, though, involves kind of what we saw from the previous solving example, but it's a little more complicated. And just diving right into it, let's kind of see, how can we write these both with the same base? Well, as it turns out, and it's not super obvious at first, takes a while to get used to it, they're both powers of 2. 8 is 2 to the 3, so that's 2 to the 3 to the x. 16 is 2 to the 4th. You can, of course, say that the 16 is 2 times 8, but that won't really get us anywhere. In fact, you can try to maybe make something work and maybe cancel out the 8 to the x's, but I don't see any immediate, there's nothing really that comes out from doing that right away. You can try that, but I don't think it's really going to go anywhere. There's not too much progress there. This is the best way of doing it. So now we can say this is using exponent properties. Remember, the biggest one being that when you have a power to a power, you multiply the powers. So this is 2 to the 3x, and this is 2 to the 4 times 2 minus x. So using the 1-to-1 property that we witnessed, we can say that 3x is equal to 4 times the quantity 2 minus x. Now we'll just solve this by our usual solving methods. Distribute. 3x is equal to, 4 times 2 is 8, and 8 minus 4x. Add 4x to the other side. We get 7x is equal to 8. Perfect. Divide by 7. We get x is equal to 8 over 7. And I'm not going to check this, but you can check this yourself, and it will work. Now getting to this one, well, are they both powers of E? Kind of. First we have to use that property, though, exponent property, that a power to a power is the powers multiplied. So this is e to the x squared minus 3 equals e to the 2x, because x times 2 is 2x. Now we can apply the 1-to-1 property and say that x squared minus 3 is equal to 2x. So even though the equation involved e, we didn't really need it because the bases were both of e. So you just drop the base basically and get to the exponents being equal to each other. Now this is a quadratic. Move everything to one side so the zero's on the other. And we'll get x squared minus 2x minus 3 is equal to 0. Factor the non-zero side. Here are factors as x minus 3 times x plus 1. Then we'll use the zero factor property. And we'll get x is either positive 3 or negative 1. And I think both of these work, and we can just check them real quick. When you plug in 3, you get e to the 3 squared is 9 minus 3 is 6. And here this is e to the 3 times 2 is 6. E to the 6 equals e to the 6. And when you plug in negative 1, you get negative 1 squared is positive 1, minus 3 is negative 2. And on the right, you get negative 1 times 2 is also negative 2. So e to the negative 2 is, of course, equal to e to the negative 2. And there we go. That does it. And that concludes this example and concludes the lecture on 5.1. I'll see you in the next video for 5.2. Thanks for watching.